Welcome to a new test and teardown video. Today we're gonna play with a configurable multimeter from HP. Actually, I'm going to make 3 videos. I will release the next couple of days, where this one is the first one. As you can see, I found a few of these, and they're different models and different configurations of more or less the same kind of idea, but we're going to start with the multimeter. So this series starts with 34, as you can see here. So HP 34, and that is the start of this series, where 740A is the display unit. 720A is the battery module. And then 702A is a multimeter module. The multimeter always goes in the bottom, batteries also always goes in the middle, and display units always goes in the top. And then you can have all sorts of different modules, for example IEEEs, frequency counters, signal generators, whatever. All sorts of modules exist, and then you have a nice little compact portable unit like this. I really hope this one works, because this one is the one with the dots as 7 segments. I can probably show you. We got 4 digits and a 1. I believe so. But I do expect to find a lot of old leaked. Oh, this one is bad. Oh, can hardly move that one. And of course I don't have any response. So I definitely need to open this before I do anything else. And here is the rear side of the unit. And of course it's very important with the power supply voltage selection. We've got 4 different possibilities. Fuse and all that kind of stuff. See, we got a little bit of calibration. And that is super easy made. Easy access to that. And that's of course our battery module and the voltmeter module. So that will be how to adjust the readout module, and that will be AC calibration for the voltmeter part of it. So now I'm gonna see if I can figure out how to. Oh, that's super easy. Oh, you just pull here, now it's falling apart. Look at that. Haha, how nice. Look at that, easy. So yeah, that is just what you have to pull. Those plastic releasers here, and then you have these interconnects, and everything just falls apart. And oh my god, I am afraid. Look at all that acid drops down into the voltmeter, and yes, the battery box is full of completely leaked cells. Oh no, that is bad. We got all sorts of fuses here and whatnot. Oh, this is just so bad. So that is something I have to see. How can I open that? And what exactly is going on? Oh, we got even more batteries up here. Look at that. So they're using the entire space with some cells up there and cells down here. And what have you got? Oh, yeah, this is also very heavy. But could I plug these 2 together and make a nice super low? No, I cannot. Because that connector here. Okay, that goes straight through and it's not doing a lot. Maybe I could plug these together. Yes, I could. I could definitely plug these 2 together without the battery module. Look at that. It is so much more cute. But of course I missed the handle. That's interesting. But I need to do a little bit deeper inspect if the acid's been dropping down into the voltmeter section, because that is how it looks like here. So yes, I have to open all this and have a look. Don't you just hate batteries in products? Are you ready to cry? Oh no. Look at that. So here, all this is acid I need to clean off. It's probably very conductive all over that place, and it's been going through those holes and down here. Not so much on that PCB, I think so. Maybe a little bit down there into what you have here with the Teflon and stuff. That is high impedance circuits. So that is of course not so good. And in here is the AC amplifier and compensation or something, stuff like that. And again, high impedance stuff is revealed by Teflon. And I can see corrosion on these, on the aluminium can here. But I think I should be able to fix that. So that was the plate that was on top of the board, and you can see it's still a little bit wet even here, right? And that is all the leakage. I need to clean this here. This is the bottom side. As you can see here, it's still a little bit wet. It has been all over the place. So definitely, I'm just gonna put this in the washing machine. And this, then, of course, this is the top, the readout module. And since this was in the top, I don't think it's been affected at all. So what I think I could do is try and power this up and see if there's any kind of light in the instrument without anything plugged. I definitely think this also contains the main power supply, right? So there's a good chance this just powers up and we can all be happy. So first I power up mains. Ooh, 40, 50 watts. 50 watts of mains entry without even powering it on. Definitely there is something shorted here. Oy, oy, oy. How is that going on? It is set for 230, 220, and this is exactly what I got on my Vario. So, oh no, there's some problem with the power supply that I need to fix before I even waste any kind of time cleaning anything up. Because if the power supply is this broken, I mean, why bother cleaning up anything? But what I like about these cases is all you have to do is release, and then you can pull out. See? The whole thing should come out if I'm doing it right. It helps pay attention to what is written here, by the way. Just in case you like to know that here's a safety ground. There was a screw going through here, and that went into that one, right? So of course it does. It didn't help me to release and pull. And yeah, it's a beautiful readout module, but I just have some sort of a short circuit somewhere here, right? So what I will do now, I will take my thermal camera and I will crank up the voltage, the input supply, AC voltage, really slow, and then I will monitor what is going on. But look what I already find. Reefer capacitors around the mains entry. And let's just start by guessing this is where to look. They're just classic for being the cause of all the problems and bad things you can imagine. Oh, this is nice. We even got some other read out LEDs or some stuff. Oh, I can't wait to get this working. It is so beautiful. And we got a crystal even. And that's probably because it's dual slope and all sorts of nice things. Oh, look at all the high impedance input. Oh, I have to go and focus. Look at that. Great. Well done. So far it's really, really beautiful. But that is not helping us a lot when the darn thing is not working. So what is wrong? Yeah, I think I've already shown you this quite a lot of times. When something is wrong with a unit like this, and I don't even have a schematic, I don't have anything at all, right? So what I've done is I have now 80 volts of mains input, and I have set the voltage switch to 240. That means my input power is about 5 watts. And of course the unit is not alive. But 5 watts is not enough to murder anything in this unit. But what I can do is I can take my thermal camera and then I can poke around like this. So what is going on? As you can see here, the main transformer, this is my finger, right? So main transformer is of course a little bit warm because the 5 watts goes in and out, right? But the only component I can see is warm is down here. Oh, it's 70 Celsius. Let's go into macro mode like that. And then you find down there 2 diodes. I think only one of them is to blame for the problem. Or is it a bridge where one of the or 2 of the diodes is shorted? Or is it because the main voltage rail is shorted somewhere else, right? So those 2 diodes down there is definitely what I want to go and have a look at first. But it can also be because power goes through some of the capacitors like that one. See? All other capacitors here, they're ice cold except for this one is a little bit warm. So we now know current goes through that one and not through any of the others. So I believe this one is the shorted, that one. The first one here is probably the shorted capacitor. That could be what we need to investigate, because how can those diodes be warm? That means voltage must be over them and current must go through them, right? So this is what we need to look at. You want to see what I just did? I lifted the mistaken or the capacitor I mistakes a little bit up like that. And then here's my ohm meter. So all those capacitors, they seems like they're in parallel. So first, of course, I want to measure down there where I solder it from. See, there is no short down there. Let's look at the capacitor. Oops, shorted capacitor. So that can explain why stuff here goes really warm. And again, I really would like to say this loud and clear. When you're playing around with old defective stuff like this, why don't you always monitor the input voltage, current, watts, and then crank it up slowly? This way you can protect your stuff, you can know what's going on, and you're going to limit all sorts of side effects. Try and imagine what would happens if I just plugged in mains and I didn't monitor anything here. Oh, this thing is not turning on. Oh, I'm pushing this and I'm pushing that. I'm measuring around. 2 minutes later, we're going to see smoke coming out of stuff. And then I burnt down the mains transformer and rendered this whole unit completely impossible to repair, right? Well, we're back with a new capacitor. And I did take a closer look on the two diodes, and I can see that they have been very, very warm. So somebody was not paying attention. My input power is now 1.5 watts in turned off mode. I believe the reason for that is that the mains transformer is of course running and delivering power to the charge systems in the battery box. So I should be able to... No such luck. And that's probably because this power on goes via some other fancy smancy things. Ew. I think it is back alive. I've just plugged in the two modules here, and I do have some readings in ohm, and in voltage I don't see a lot down in the lower voltages. So this is the 1000 volt range. I do get some blinkety blinky. I think this is error something, and this is, it's showing negative, and I'm coming with positive, and it's of course, see, this is 1 volt, 2, 3, 4, 5 positive input. So yeah, there's definitely a lot of stuff wrong, but I need to clean up all the leakage, all this battery acids all over the place, and then it's probably gonna work a lot better. But it looks promising so far. So we had a few missing screws and a piece of metal down here. Look at all the leakage damage and a little piece of isolation material. Ooh, gross. Isn't it a little bit funny to see all those different cells? So maybe we got 8 cells here, we got 8 cells here, and I believe we got 4 cells here because I can feel... Oh, maybe we also got 8 cells. But there's a different all of them, I guess, right? But I need to get all this out and deep clean it. And of course, we're not gonna run this thing on batteries anymore. That's completely stupid. But I really would like to restore it into just a little bit of a working condition. I think it calls for a little celebration. You can see all my problems are gone, and this thing is now measuring voltage correctly. I must say I was getting a little bit frustrated. This is a very, very complicated circuit. Oh my God, I look so much forward to see if I can explain you guys how it works. And also maybe I can explain with a little bit of luck how I figured out the error. So first, let me show you the circuit board here. There's this IC here called U9. This is the magic custom part they made. And that one is like a time counter. So it's counting the result from the dual slope converter, and the dual slope converter is using those field effect transistors to start and stop the charging of this capacitor here. So it's a very big film capacitor, and it's right there. We got some op amps that's doing the integration currents and the feedback for all that. Here we can measure the ramp of the integrator. We got the zero detector signal right here. And all that is working, and it was working. So let me try and zoom out on the scope here. Here we go. So that will be the integrator ramp on the slope. So we got, at the moment we got 12 volts input. Let me try and change the input voltage. So now you can see what happens, right? This is only 2 volts. So the first time here is the voltage we are measuring. And those pulses up here, they are the ones that control all the timing in this entire system, that do 0, auto 0, the ranges for all this. They are also doing those pulses. They come from the U11, and that circuit didn't work. This consists of 4 NAND gates with open collector output, and I was lucky to have 2 of those in my little stock. I was going through some other parts here. Those are the 00, and that will be 03, because I thought that maybe if it is not that one, then I'm gonna go for the next one. So this is U11 and this is U10. But I was lucky, my first guess was the correct one. So this one is generating pulses that clocks the positive and negative sign, and that is measured here on some test points on U16. And I did not get any response here on that, the positive negative output signals of U16, and because I was missing clock. And by the way, normally this unit works on 30 Hertz updates, but I live in 50 Hertz land, and for some reason the pulse detection and all that stuff is now working on 50 Hertz and not 30. That will be, of course, half the mains input frequency, because of course a voltmeter is synced to mains input frequencies, and that is a good way to minimize noise and all that kind of stuff. So that is definitely always the case with good quality voltmeters. And this one syncs to 50 Hertz without any division or anything like that. And in the schematic, I could see that the pulse was supposed to be 30 microsecond long, but it was only 10 microsecond long. Now I put in a new IC. So what I've done is I've adjusted this capacitor here to, I've added this on top of the 10 nano. I put a 22 nano film capacitor on top of that one. So let's look at the oscilloscope again here. So that will be the pulses here on the purple. And we got 10 microsecond pulses. See? 10 microsecond per division, right? So this is almost 30 microsecond. And by changing this value, I also get a little bit more accurate output or reading. So that is just so fantastic. Of course, I'm gonna go through a full calibration. So here's my 12.345. But I'm of course gonna go and check everything else if everything else is perfectly fine. But this is more or less how I was able to find the problem and solve it. By the way, I really want to show you how this voltmeter really works. So here I will show you a schematic of the brainy part of the schematic. If you want full schematics, it's super easy to go online on HP Archive or similar sites and get the schematic. Let's look at the business end first, right? So the readout is a dot matrix. It's not a 7 segment completely. It's just a dot matrix with all those enable lines. The common anodes are here, and those drives one line plus a little bit, one line plus a little bit, like that, right? So those are enabled one by one in the multiplex system, and here is a demultiplexer or a 3 input and all those outputs, right? So this is how each of the individual elements, they are enabled one by one. But then as you can imagine, it's a little bit funny. Each 7 segment is lit up half and then the other half, left and then the right part. I think that is a little bit funny, isn't it? And then the other row, the horizontal row, is driven by a character generator. And that character generator is gets the BCD input via all those gates and stuff, because there's also some blanking and some over range and all that kind of stuff involved. So this is done by this. And all this is, of course, in sync to read out the content of all the counters in the data accumulator. This is what they call this fantastic U9 special custom IC. So this is what converts the time of the slope converter into a readout voltage. Isn't that fancy stuff, huh? So that will be the select signals, and that will be the data. And then they go to the character generator. I think this is amazing. And then, of course, you have the polarity is read out by this little display here. And that is this nice display. They got a little individual display right there. And this can do positive or negative. Let's see if it's the same kind of readout. If I, oh, it is. That is amazing. And here is the battery box. Now I removed all the leaked batteries and completely cleaned it. I nearly licked it clean all the way around. And when I showed you this before with all the leakage and all that kind of stuff, you also maybe noticed all the missing screws. And I happened to keep all my inchy screws for stuff like this. So I got a big collection of special inchy screws, and that is a little bit special. Maybe I'm crazy, but this is this is what I got, so I can repair stuff like this. You need those screws. You can't even tell which ones I replaced, because I just happen to have the right screws for all my HP equipment. Yes, this is not me who lifted this, probably a charge resistor, and the board is just completely dark and burned where this resistor was located. So probably what happened was the cells shorted, and then you go into charge, and then this resistor just burned the PCB, and then some lazy dummy simply just lifted the charge resistor and used it in line only mode. Instead of doing it right, remove the damn batteries, and then I could have saved a long time if it was done correctly. I like you to see what they have done in the manual. It's really nice. They delivered 27 test points, and not only with all the curves and detail explains, they also say what could be the faulty components. So it was real easy for me to track down the problem. They also showed component placements with all those test points marked. So it's super fast and easy navigation around the board. Definitely something that you will find in an HP service manual like this, top quality. Here's a little snip from HP Archive from the product flyer from 1974 or something like that. They show a little bit from this HP 74 740 system, the snap together concept like they call it. And here they show a different model. I don't have this voltmeter stocked here, but they show, oh, it's the 1973 catalog. Yes, that is exactly what it is. Some of the modules, they are from 1974 or 1975, I guess. And that is what made me a little bit confused. They say this voltmeter only uses 5 watts, but my unit uses about 10 watts. So yeah, you got many different versions of snap-in modules. You can configure your own. Here's a picture from the service manual I found that shows some different display modules, different battery modules, and DC voltmeter module, multimeter module, and a DC amp ohm meter module. So there's only one last thing to say. Now it's completely assembled and ready to go. Thank you very much for watching. Hope to see you soon again. Bye bye.